So the whole point of making a statistical model of data is so that we can make decisions. So now let's talk about how we can make inferences based on the information that we get from a regression analysis. But first, let's start with what statistical inference is. So that's going to be the process of making estimates and drawing conclusions about one or more characteristic of a population through the analysis of sample data drawn from that population. So if we're looking at regression, we're making inferences about the regression parameters beta naught, beta 1, and so forth. And so the mean value or the predicted value of the dependent variable y for specific variables of the independent variables of x1 star, x2 star, so forth. So we're going to consider both hypothesis testing as well as interval estimation when we're doing this. And so when we're working with the multiple linear regression or least squared regression model, there are certain conditions that we need to meet in order for our assumptions to be valid. So for any combination of the values of our independent variables, the population of potential error terms needs to be normally distributed with a mean of 0 and a constant variance. Another thing is that the values of E need to be statistically independent of one another. And so what this looks like is we have a model of these conditions and their implications for simple linear regression. So note that in this graphical interpretation, the value of E of y of x will change linearly across the specific value of x that's being considered. And so the mean error is going to be 0 at each value of x. However, regardless of the x value, your error term E, and therefore the dependent variable y, are going to be normally distributed, each with the same variance. And so the specific value of the error term E at any particular point is going to depend on whether the actual value of y is greater than or less than E of y of x. And so here we have a simple scatter chart of the residuals and independent variables, which can be an extremely effective method for assessing whether or not these conditions are violated. We should review the scattered chart for patterns in the residuals indicating that one or more of the conditions have been violated. Ideally, the residuals will be consistently scattered around 0 throughout your predicted values of your independent variable. The residuals in the 4 panels here show distinct patterns, each of which would suggest a violation of at least one of the regression model conditions. So if we look at panel A, the variation in the residuals increases as the value of the independent variable x increases. This suggests that the residuals do not have a constant variance. If we look at panel B, the residuals are going to be positive for small and large values of the independent variable x, but we have negative for all the other independent variables. This pattern is going to suggest that the linear relationship in the regression model underpredicts the value of the dependent variable for small and large values of the independent variable and overpredicts the value of the dependent variable for the intermediate values of the independent variable. If we look at panel C, they're not symmetrically distributed around 0. So we see many of the negative residuals are relatively close to 0, but we have relatively few positive residuals that tend to be far from 0. So this skewness suggests that the residuals are not normally distributed. And then if we look at panel D, these residuals are plotted over time t, which generally serves as an independent variable, but here we have with an independent variable, the observation is made at each of several usually equally spaced points in time. You can generate scatter charts of the residuals against each independent variable in the model when you can use Excel's regression tools, and if you do that, you could use the residual plots option in the residuals area of the regression dialog box. Here we see the residuals plots that were produced by Excel from the Butler Trucking Company example, where remember our independent variables were miles and deliveries. Miles was X1 and deliveries was X2. The residuals at each value of mile appears to have a mean of 0. It also appears to have similar variances and appears to be concentrated around 0. The residuals at each value of the deliveries also appear to have a mean of 0 with similar variances and a concentration around 0. These are all good things for us to use, be meeting the assumptions needed for multiple linear regression. So when we're testing our individual regression parameters, we need to determine whether we have statistically significant relationship between our dependent variable and each of our independent variables. So if our beta weight is 0, that means that we don't have a linear relationship between the dependent variable and its independent variable. And if the beta value is not 0, then that means we do have a linear relationship. And so when we do this, we're going to use a t-test to evaluate this. And so as the magnitude of our t-value increases, we are more likely to reject the hypothesis that the regression parameter beta sub j is 0. And when we reject the hypothesis that the regression parameter beta sub j is 0, we can conclude that a relationship exists between our dependent variable y and the independent variable x sub j. Oftentimes when you use statistical software, it will generally report that p-value for the t-test statistic for you. And for a given value of t, your p-value is going to represent the probability of collecting a sample of the same size from the same population that gives you a larger t statistic, given that the value of beta sub j is actually 0. Your hypothesis in this case is that your beta sub j is equal to 0, and we're going to reject that when the corresponding p-value is smaller than the predetermined level of significance, which is usually 0.05. So to test that beta sub j is 0, meaning that there's no linear relationship between x sub j and y, at some predetermined level of significance, typically 0.05, the first thing you're going to do is build a confidence interval at the 1 minus 0.05 times 100% confidence level. So if the resulting confidence interval does not contain 0, we can conclude that beta sub j differs from 0 at the predetermined level of significance. Similarly, if we're going to test that beta sub 0 or beta naught is 0, which would basically mean that we're testing that the dependent variable is 0 when all the independent variables, x1, x2, x3, whatever, are equal to 0 at some predetermined level of significance, typically 0.05. First thing you're going to do is build a confidence interval at the 1 minus 0.05 times 100% confidence level. And so if the resulting confidence interval does not contain 0, we will conclude that beta naught differs from 0 at the predetermined level of significance. When we're looking at non-significant independent variables, if it is practical to keep it in there, then go ahead and leave it in there. If the model is sufficiently explained without that non-significant independent variable, take it out. And the appropriate treatment for the inclusion or exclusion of your y-intercept when b sub 0 is not statistically significant may take some consideration. But note that it's possible that the estimates of the other regression coefficients and their p-values may change considerably when you remove a non-significant independent variable from the model. And since the primary purpose of your regression model is to explain or predict values of your dependent variable or values of the independent variables that lie within the experimental region on which the model is based, regression through the origin should not be forced, meaning you should not get rid of your y-intercept value unless you have a strong, what we call a priori reason, or you have a strong theoretical background to justify believing that the dependent variable is equal to 0 when the values of all independent variables in the model are equal to 0. One of the other things that we need to think about with multiple linear regression is the concept of multicollinearity. And so this is going to refer to the correlation among the independent variables in that multiple regression analysis. Basically, if they measure the same thing, they're either going to inflate your R value, your R squared, or they're going to deflate your R squared value, but nonetheless, it's going to mask how much is actually explained. So according to a common rule of thumb, multicollinearity is a potential problem if the absolute value of the sample correlation coefficient exceeds 0.7 for any two of the independent variables. The primary consequence of multicollinearity is that it's going to increase the variances and standard errors from your regression estimates of your beta weights and predictive values of your dependent variables. So this interference based on these estimates is going to be less precise than it should be. So when we're looking at inference and regression, inference in very large samples, so when you have, let's say, population level sample set, virtually all of the relationships between your independent variables and dependent variables end up becoming statistically significant. So if your sample size is sufficiently large, your inference is no longer used to discriminate between meaningful relationships. And so this is because the variability in your potential values for your estimators of a regression parameter beta will depend on two factors. So factor one, if the values of xj and y consistently adhere to the relationship between xj and y that is applied by beta sub j, there will be relatively little difference in potential values of b sub j that can be generated by different random samples. If the values of x sub j and y do not consistently adhere to the relationship between x sub j and y that is implied by beta sub j, there is a potential for relatively large differences in the values of b sub j that can be generated by the different random samples. Factor two is if the sample size used to estimate the regression model is very large, then almost no difference in your potential values of b sub j can be generated by different random samples. And so there will also be almost no difference between your potential values of the estimator b sub j and your regression parameter beta sub j. So when we're looking at our overall relationship, we're going to use our f-test just like we did with our previous examples when we looked at ANOVA, right? So that if the f-test leads us to reject the hypothesis that the values of our beta weights are all 0, you're going to conclude that there is an overall regression relationship. Otherwise, you're going to conclude that there is no overall relationship. Now, if you conclude that there is no overall regression relationship, then the beta weights that you get in your parameters estimates table are pretty much useless. So here when we're looking at our F statistic here, the numerator of this test statistic is a measure of the variability in the dependent variable y that is explained in our independent variables x sub 1, x sub 2, so forth. Our denominator is a measure of the variability in the dependent variable y that is not explained by our independent variables x1, x2, so forth. Typically, if you're using statistical software, they will generally report that p-value for your f-test statistic. But for a given value of f, the p-value is going to represent the probability of collecting a sample of that same size from the same population that yields a larger f statistic given that the values of beta 1, beta 2, so forth are actually 0. Therefore, if you have a smaller p-value, that's going to indicate stronger evidence against the hypothesis that the values of your different beta weights are all 0. Basically, that means that you have stronger evidence of an overall regression relationship. So basically, when you get the ANOVA table for a regression, you want your F to be big and your P to be small. And therefore, your hypothesis is going to be rejected when your p-value is smaller than your alpha, typically 0.05, and that's going to be considered your level of significance. So now let's take these assumptions and relate them to our North American copier sales that we looked at way back when we were doing correlation. So we can predict the number of copiers sold from a selected value of number of sales calls made. Okay, so let's review the assumptions. They have to follow the normal distribution, has to have a mean on the regression line, has to have the same standard error of the estimate, and they need to be independent of everything else. Okay, so when we're constructing our confidence intervals and prediction intervals, you're going to use a confidence interval when the regression equation is used to predict the mean value of y for a given value of x. So we can have two different predictions that can be made for a selected value of an independent variable, and a confidence interval and a prediction interval. So in a confidence interval, the width of that interval is going to be affected by the level of confidence, the size of the standard error of the estimate, and the size of the sample, as well as the value of the independent variable. The prediction interval is also based on the level of confidence, the size of the standard error of the estimate, the size of the sample, and the value of the independent variable. The difference between these two variables is the 1 under the radical. So we just have 1 plus everything, or just 1 over n plus those values. And so the prediction interval will end up always being wider than our confidence interval. And so when we do this and we're comparing them, we're going to find a t-value. So here, the degrees of freedom is going to be n minus 2. So 15 minus 2 is 13. We're going to set the confidence interval to 95%. Find the value of t. We're going to move down the left-hand column of our t distribution table to 13 degrees of freedom. Move across the column to the 95% level of confidence, or an alpha 0.05. Where we get a t critical value of 2.160. And earlier we calculated that the standard error would be 6.720. So we're going to let x equal 50. And the mean number of sales calls is 96 times 1440 divided by 15. And so the sum of my x minus x bar squared is going to be 25. So we end up with 600. So we're going to insert the values into our formula and we solve, and we end up with our value being, our prediction interval being 33.0032 plus or minus 16. And then our confidence interval is 33 plus or minus 6. So the thing that I want you to notice here is that the interval for the individual is quite large, which is much larger than the interval for all of our sales representatives combined. And so when we're trying, another thing we need to think about is maybe transforming our data. So sometimes our data doesn't quite do what we need it to do, and so when we're looking at this, we have regression analysis, and the correlation coefficient will require the data to be linear. What if your data is not linear, right? If your data is not linear, we can then rescale one or both of our variables so that we can force us to have a linear relationship. So a couple of things that we can do, we can take the log of one of our values. Typically it's your y variable. You can take the square root of one of your variables or both your variables. You can kind of play with the reciprocal, or you can square one or both of the variables. But so that what type of transformation you do kind of ends up being a little bit of trial and error. But when you are, the thing to keep in mind, if you have to do a transformation on your data, is that when you are interpreting that correlation coefficient or your regression equation, Sometimes you're not interpreting a linear relationship. And so, for example, like if you were using the actual values of the dependent variable y, you might create a new dependent variable by transforming it, and then you've got a relationship of, what happens with your x to the log of your y. Then you've got to kind of do a little bit more explaining about the relationship between those variables. So here we have an example of transforming our data. We have Groceryland supermarkets trying to determine whether there's a relationship between the selling price and weekly sales. And so, is the relationship direct or indirect? Is it strong or weak? So to determine this, can we effectively forecast our sales based on our price? So here what we need to start with is we need to decide what's going on. So here it looks like we have a strong relationship between our two variables. We have, based on our output, we have a coefficient of determination is 88.9%. So remember, this means that 88.9% of the variation in sales is accounted for by the variation in price. But be careful, because if we look at our scatter plot, we see that the relationship's not quite linear. So that means we might need to transform our data. So the director decides that we're going to do a log transformation, and so and this allows for us to increase the coefficient of determination from 89% to 99%. But now price explains almost all the variation in the log of the sales. So our transformed data is going to fit a linear relationship, but when we talk about things, we're going to have to undo that transformation by taking the anti-log of our values to find that if they price their cola at $1.25, they'll sell 39 bottles, and at $2, they'll sell 9 bottles. So with this transformed variable, we can clearly see that as price increases, our sales decrease. And this relationship can be very helpful to Groceryland when they're making pricing decisions about their product.